This is the section on the hyperbola, and this is actually my second take. I usually try to get it done in one take because this is a lot of work. During my first 2 minutes that I recorded here, I previously and then deleted, I kept misspeaking. I used other words for hyperbola, and I just don't want to do that. So here's the hyperbola, and this is how it looks like. We're already familiar with a few of these words, so they're the foci and the vertices, and then this is how it looks like. In fact, this is a hyperbola that opens sideways, and look at these distances d1 and d2. Back when we looked at the ellipse, these two being added would be a constant, and we get the ellipse. Previously, these two were actually the same, and we got the parabola. So depending on what you do of these two distances, d1 and d2, you get different curves. In this case, on the next page, they're deriving the equation for the hyperbola, and here we go. In this case, they actually subtract the two. They come up with plus minus 2a, and that again is constant, and then they go to the derivation, and here we come up with the equation, standard form of the equation of hyperbola with the center at 0, 0, and this almost looks like the equation of an ellipse. The big difference is for an ellipse there would be a plus here. For hyperbola there's a negative in front of one of the two, not both, but just one. So when the negative is in front of the y squared, we get a hyperbola that opens sideways. If the negative is in front of the x squared, we get a hyperbola that opens up and down. And that's what they are saying exactly here. So this is the sideways one, and then this was the up and down one. And notice the difference is y squared minus x squared, and over here it's x squared minus y squared. This one is the one with the center at the origin. I mentioned earlier, I like the general case better because there you can shift the center to any point hk. I think they should just leave the other one out and just do this one. So this one here is the standard form of the hyperbola centered at h and k, and then these denominators mean something here. They tell us how far the vertices are from each other, and they also tell us how wide each part of the hyperbola is opening. By the way, you do see a gap in here between where the hyperbola is not defined apparently. Well, that's easy to explain, that if you choose an x that is sufficiently smaller, and this whole thing here is smaller than 1, then you can subtract whatever you want. You're never going to get to 1. So therefore, yeah, you cannot be in that region. And the same thing over here with the y. Earlier for the ellipse, by the way, I forgot to mention that it was that as you add the two, if one of them already is larger than 1, then you cannot, whatever you add, you're never going to get back to 1. So that's why the ellipse has actually maximum values, while the hyperbola has kind of minimum values. All right, let's see. So find the equation of hyperbola with a vertex. So here they're going through the motions. They say, okay, we got a vertex here, and they're actually starting out with the foci 4, 3, and 4, negative 7, and a transverse axis of length 6. And by the way, in my home office here, my neighbor is using the bandsaw, but what can you do? That unfortunately distracts me. So going through the motions here, and they're using this table here to figure out all the other things here. So here's the center then, 4, negative 2. And then here's that parameter c that is being used in order to figure out what a and b are. Respectively, a is already given. And then this one here is actually the equation of the hyperbola. So with the y plus squared here in the front, that is actually a parabola. There I go again. Hyperbola that is opening up and down. I guess I don't use the word that often. All right, so let me go over to Desmos. And I didn't make my own. I'm using somebody else's. So I just have to remember these numbers here. I have here a negative 2 and a 4, and here I have a 3 squared and a 4 squared. I remember that. And I have the y squared in the front, and the x squared here has the negative, which is why this one opens up, down. Okay, let's go over to Desmos. And so here it is. And I actually have to change something here because the person who prepared that actually produced a sideways opening hyperbola, but it's actually really easy to change this one here. So negative, and Scholl is her name. Usually you don't see credits on Desmos, but in this case I did. So here's the up and down opening hyperbola. Notice as I change that, let me go back. Here, by the way, here are the foci points. This little square here is a helping way in constructing that, and so are the asymptotes. I will show that when I actually have my hyperbola. And then the circle here, which by the way is not in the book. The box is, and so are the asymptotes, just not the circle. But with the circle, we can figure out where the foci are. Notice that the foci are here within the hyperbola and over here as well. So when I change this one here, there we go, and here we go. And now it's opening up and down. I actually have to change my foci as well. They're supposed to be here and here. So let me do that. Let's see, it's down here. Here they are. And this should actually say focus. There we go. And I'm going to change this one here. The plus C actually goes here. There. Did you see it pop up? And the minus C should go here. And that's really these two things I need to fix, the focus here as well as the negative in front of the x squared or y squared. Okay, so for the k, I have a -2, I remember. So it's pushed over here. Oh, I said k, didn't I? -2, so down, that makes sense. And then for the h, I have a 4, so over there. Looks like it's out of the picture, so I'm going to get it back. There it is. And then for the for this one here, for the y squared, I had a 3. I know I could also write it like this. Let me do this. Control X. And put that actually in the front. Control V. There we go. There we go. Okay, now it's not confusing me so much. So for the B in the front, I have a 3. There we go. And for the A, I have a 4. Whoa, this is big all of a sudden. There we go. Better zoom out so I can actually look at it. And let's compare what we have in the book. So notice the center is down here at 4 and -2. And then the foci are up here and down there. And then the asymptotes and then the hyperbolas here. So let's check. And that's the way it looks. Right on. So here, okay, let me explain this little box here. If you were to graph the hyperbola by freehand, this is what you would do. You would find the center first, then you would use the A and the B. Notice the A is 4 and the B is 3. So start with the center, measure the A, 4 to the right, 4 to the left, measure the B, 3 down and 3 up, and you get this little box. Then what you do in this box, you draw these two diagonals through and extend them outside of the box. And then you use these diagonals as asymptotes. And then you draw here the vertex of the hyperbola, and then you kind of carefully draw it here so that it becomes asymptotic over here, asymptotic over here. And then you do it with the one down here as well, asymptotic over here, asymptotic over there. So it's actually really slick to use that little box. The circle comes in to say, okay, I got a radius here for this particular circle is half the diagonal, and then I use this is the protractor, it's a compass, right? So I use a compass in order to draw that circle here, and then at this point right here, vertically below or above, that's where the foci are. So as I said, that's pretty slick. All right. Here they have more examples coming up, and then they actually do have an application here, this kind of thing here, application to sculpture. And I actually did find this one here. I had it in my German video that I posted for fun earlier. So this is a May West. It's an art exhibit in Munich in Germany, and there's actually a tram and a highway going beneath it. It's actually named after the actress Mae West, I guess, because of the of her figure back 70 years ago. And so here you see the hyperbolic one. Besides art, we can also look at, let's see, where did I have it? Here it is. Oh, actually, I do have it here. Cooling towers. Actually, they look like that too. I know this is the German one. They look hyperbolic, but when I go to the English one, we can see them again here. And then when I scroll a little bit down, it actually tells me, or it did so earlier. I was hoping I'd find it right away. Oh, there it is. Airflow generation methods. Oof, okay. Hyperboloid cooling towers have become the design standard for all natural draft cooling towers because of their structural strength and minimum usage of material. And the hyperboloid shape also aids in accelerating the upward convective airflow, improving cooling efficiency. And then they're probably associated with nuclear power plants. However, they can also be used for coal-fired power plants. So that's where you encounter hyperbolas on these kinds of cooling towers, for example. All right, let's go ahead with a couple of exercises. I chose number 20 and 22. I'm going to do 22 first, simply because I already have the y squared in the front here, and that's actually what it shows in Desmos already. So I have my center is at 4 and 2, and my B and A, I guess, are 5 and 3. I think we can see that. So I'm going to go in there. What was it again? 4 and 2 is the center. 4 and 2. And then the one in the front of this one here is a 5 squared, and then this one is a 3 squared, so the B is 5. There. And the A is 3, right? Okay. Let me actually show you with that box a little bit better. I'm going to turn some stuff off. I'm going to turn the, actually I'm going to leave the center there. I'm going to turn, yeah, these things off here. And let's see. Cool, cool. Cool, all right, okay. Basically, I turn everything off. Except the center. Leave that on. Everything is off. Okay, so here's the center. And then I'm going to use these A and B here. So 3 to the left and the right, and 5 up and down. And that's what I'm going to try to show here. I believe I do that. So 3 to the left and right. 5, that's a little bit off the screen. There it is. So this, by the way, I'm clicking off screen. It's right next to that. Here are the buttons, you know. So here's my little box. Now I'm putting these diagonals through. These are these here. And these are also become the asymptotes. And then I can actually draw the hyperbola. Now, of course, I need to know that my hyperbola is up here and down here and not on the sides. But I do know that from the y minus k squared here being in the front and the negative being in front of the x squared. So when I click that one here, you can see, okay, here's the vertex, and then it becomes asymptotic to these diagonals, and you can see these here. There we go, getting closer and closer. And of course, doing the same thing on the down here. And then what they're doing is they do this circle again that is actually not in the book. Let's see where the circle, oh, here's the circle. Nice equation for a circle, right? X squared plus b, x squared plus y squared equals the radius squared. And here it is. And of course, the h and k is simply because the center is at a different place. So there it is. And that's what is then being used to determine where the foci are, right here and right there. So I think that explanation came out a little better than what I did earlier.